So let's consider problem 8.50 of Sonntag, in which we have a cylinder containing R134A at 10 degrees Celsius and 150 kilopascal. So we have a piston cylinder arrangement which contains R134A, state 1, T1 equal to 10 degrees Celsius, P1 equal to 150 kilopascal. The volume at the conditions prevalent is 20 into 10 raised to minus 3 meter cubed, because it is 20 liter. A piston compresses R134A in a reversible isothermal process. So this piston is loaded with something, maybe some force, and then it is compressed to the state 2. The state 2 is saturated vapor. So x2 is equal to 1, and it is an isothermal process, so T2 equal to 10 degrees Celsius. It is given that the process is reversible and isothermal. For a reversible isothermal process, ds equal to del q by t, which implies q12 equal to t multiplied by S2 minus S1 is equal to T multiplied by mass multiplied by S2 minus S1. This is the total quantity, this is the specific quantity. Okay, so this will give us, so we know all the properties needed to find the mass, we know the volume, we know the initial T1 state, the state 1 and the state 2, so this can be easily found out. Similarly, we want to find out the work done. So Q12 equal to mass times U2 minus U1 plus W12. These can be found out because we know all the state points. Similarly, this is known from the previous result, so the work done can be found out. It's a very straightforward process. Problem 8.50. T1 is equal to 10, P1 is equal to 150, volume is equal to 20 times 1e minus 3, mass equal to volume by specific volume at state 1, specific volume at state 1 equal to volume of R134A, T equal to T1, P equal to P1. Okay, S1 is equal to the entropy, copy this. Similarly, S2 is equal to, okay, so T2 is equal to 10, x2 is equal to 1, and so the S2 is equal to entropy of R134A at T equal to T2 is equal to x2. So Q12 is equal to T1, so the T has to be in Kelvin, 273.16 times mass times S2 minus S1. So this T is in Kelvin. Okay, this is very important to note. Similarly, using the first law, Q12 equal to mass times U2 minus U1 plus W12. This will give us the work done because Q is known from this state. So we go up and write down the expressions for the internal energy. Similarly, copy this. Okay, so the work done is minus 3.816 kilojoule. The heat transfer is minus 3.837. So heat is lost by the system and work done is on the system. Okay, just by looking into the problem, can we devise how the process looks like in maybe the PV or the TS diagram? So initially we had some superheated, this is superheated because we don't bother with X, we have T1 and P1. So one does not need to take my word for it whether this is superheated or not. We just go to plot, property plot, we go to R134A and we go to maybe PV diagram, and we include line of 10 degrees Celsius. Okay, so this is the line of 10 degrees Celsius and it is P equal to 150 kilopascal. So this is okay, let me just enlarge the window. So if this is 100 and this is 1000, 150 is somewhere here. Okay, it's in the superheated region. We have been given that the process is isothermal. Okay, because of that it starts here and maybe reaches here because it is 10 degrees Celsius and X equal to 1. So possibly, not possibly, this should be the second point. Somewhere here should be the first point. 150 kilopascal and 10 degrees Celsius, then it is compressed so that it is isothermal, which is 10 degrees Celsius, which is this line, and saturated vapor. So let's see, let's go to plot, overlay plot. So P versus V. Okay, so we don't have the specific quantity, so we have the volume at this state, we don't have the volume at this state. So let us just, for the sake of plotting, find out the specific volume at point 2. Okay, so we go to plots, overlay on the x-axis we have the specific volume and on the y-axis we have the pressure. Okay, there is some error in which E is because we have not run the program, it is not able to determine what the volume is. So we must make the plot again. We had to run the program because after changing we did not run the program. So we go to plot, property plot, R134, line of 10 degrees Celsius, very good. We go to plot, overlay plot. On the x-axis we have specific volume, on the y-axis we have the pressure. So the pressure is not known. Okay, so the pressure is not known. So we must find out the pressure in order to plot P2 equal to pressure. Okay, very well. Okay, now we have both the pressure and the specific volume. Overlay plot. Okay, there we go. So where is the first point? Okay, we must extend the x-axis. So the maximum of the, so minimum, let's make it as 10 to minus 3. And the maximum as 1 is 0. Okay, there you go. This is the first point, this is the second point. It's an isothermal compression process in which the pressure is increasing. Look, the pressure has increased. This is so the pressure initially was 150 kilopascal, it has increased to 414.9 kilopascal. This is the consequence of a compression process which is isothermal. So during the isothermal compression process, because if we do not let heat transfer to take place, simply compression will lead to a temperature increase. But we want the process to be isothermal, that is why we have to extract some heat. That leads to a negative heat transfer, that is, heat is extracted from the system. Similarly, work is done on the system. Okay. So this is the concept. We have used the second law to find out the heat transfer for the reversible process. Similarly, we have used the first law to find out the work done.